Today we are looking at the last section of multiple integrals. What are we going to do here? We're going to learn how to change variables. Now you have already done a bit of that in the previous lectures. We have changed the x and y rectangular coordinates to polar coordinates in double integration. And in triple integration we have also changed to cylindrical and spherical coordinates. And remember, I told you when you made that change, right, you multiply by something called the Jacobian. So whenever you have to change variables in multiple integration, you must multiply by the Jacobian. So this lecture deals with the Jacobian and shows you how to change variables generally. Not necessarily polar or spherical, just generally. How do you change variables? Now, why do we want to change variables? Think of Calc 2, right? When you had a difficult product or quotient to integrate and you had to use substitution. Why did you have to use substitution? Because you wanted to trivialize the integral. You wanted to make it a lot simpler to integrate, right? So why do we change variables in multiple integration? To make the integral a lot simpler. Okay? Right, so let us look at what we have done from what I've spoken about, remember. So this first integral here, these were polar coordinates, and the second one was spherical coordinates. So let me just outline. Remember these, this, and this were called the Jacobian. Okay. So let me give you the definition of the Jacobian. So what we have, let me go back to my black. So what we have a region. This is what we're doing, right? We have a region with x, y coordinates, right? And we want to transform it to a recognizable region. So let me take out this. You want to transform it to, say, a recognizable region in the UV plane. And this is the transformation. Okay, so I'll say this again. You have a double integral or triple integral to find over a region. And this region, it's very hard to integrate over it. So transformational variables will transform this region into a region that is a lot simpler to integrate over. And the simplest one is the rectangle. That's why I put it there. Okay? So the change of variables is determined by a transformation from xy to uv. Now this is the definition of the Jacobian. So it is denoted by J, and it's del xy over delta uv. That is the definition. And how do you find it? You use determinants. So you find the partials and you find the determinants. So it's partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Find the determinant of this, and remember the definition for determinant of a 2 by 2 matrix. It would be partial x, partial u times partial y, partial v minus partial x, partial v times partial y, partial u. So the Jacobian is a determinant. So let's find some Jacobians. I'll show you how it's done. Find the Jacobian from converting from rectangular to polar coordinates. So remember, going back, what was our Jacobian? Can you remember what it was? When we converted to polar, what did you have to multiply by? R. So your Jacobian was R, right? So I'm going to show you how you find R. So first of all, you need to write out the formulas that you're going to use to convert. What is x equal to? What is y equal to? So x is equal to r cosine theta and y is equal to r sine theta. So here you have x and y in terms of two variables, r and theta. So the Jacobian is therefore defined by, so you put delta the xy on top, and below you put the variables or the parameters that are used. So delta r theta. So that is the definition. Then you set up the determinant. So you want to put a 2 by 2 matrix in there. What is the first partial? So just go according to the definition here. So it's partial x, partial r. Then on the same row, it's partial x, partial theta. If there was a third variable, you'd continue on the same row. Next row now do the y's. Partial y, partial r, partial y, partial theta. Okay? Now you find these partials. So can somebody tell me what is partial x, partial r from this equation there? You're going back to partial derivatives, eh? Cosine theta. What is partial x, partial theta? Very good. Minus r sine theta. Good. So don't just leave, you're not finished with partial differentiation, right? Even though you are doing integration. Okay? Next line. What is partial y, partial r? Sine. Good. What is partial y, partial theta? Say it again. R cosine theta. Come on, sound sure. You know this. You do. Now let's work out this determinant, right? So r cosine theta times cosine theta is r cosine squared theta minus negative r sine theta by sine theta is minus r. So that's a plus r sine squared theta. Simplify this. R times cosine squared theta plus sine squared theta, and that is r. So that is how you work out Jacobians, right? All right. Any questions? Okay, let's do another one. Find the Jacobian given, and so you have the formulas for x. So notice x and y, they are both given in terms of u and v. So set up the definition first. So j is equal to partial x or delta xy over delta u v. Okay, so you put the xy on the top and you put your parameters on the bottom. It's like a fraction, right? Now write the determinant, the 2 by 2 matrix. So it'll be partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Okay, let's work this out. Can you tell me what partial x, partial u is? 5. Partial x, partial v. Partial y, partial u. 3. Partial y, partial v. 1. Good. Now work that out. 5 times 1 is 5 minus 3 times 2 is 6. So this is negative 1. Let's do this one. So set up the definition first. So write it down and then you set up your matrices, okay? Your matrix. So delta xy on the top, and then always put your parameters on the bottom. That is your J. The matrix again, partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v, partial x, partial u is, tell me, partial x, partial v, partial y, partial u, 2v again, partial y, partial v, 2u. Let's work that out. That is 2u times 4u squared minus as a plus 4v squared. Any questions? Okay, it's your turn, is it? Did I say do now? I did. So you have 2 to do. So try them on your own. Okay, so the same thing, J is delta xy over delta uv. And this is the determinant. Again, no difference here. And then, as you got, this is 5 minus 1, 1, 3, which works out to be 15 plus 1, which is 16. Wonderful. And the same thing here. So J equals the determinant. Partial x with respect to u is v. That's a u here. Y with respect to u is 1 over v. With respect to v is minus u over v squared, which works out to be minus u over v minus u over v, which is minus 2u over v. Okay? So as a first step, you need to be able to calculate Jacobians. All right? So that's the first step. Let's move on. Now let's learn to transform regions. Okay? So remember what I told you, what the change of variables would do? You would take maybe a non-trivial region, use a change of variables, and transform it to a region that you can easily integrate over, like a rectangle or a right angle triangle or a circle. All of these are easy to integrate over. Okay? So let us see how you apply that transformation to the old region to get the new region. So determine the new region by applying the given transformation to the region R. So what is R? It's an ellipse. X squared plus y squared over 36 equals 1. And the transformation that you are using is x equals u over 2 and y equals 3v. Now, if you had to integrate over an ellipse, that would be a little difficult to do. I mean, it can be done, but it would be difficult. But let's transform it using our transformation, our equations there, and see what we get. So how do we transform? Just by substitution. So you replace x with u over 2 and y with 3v. So let's see what you get. So you get u over 2 all squared plus, and then you have a 3v all squared over 36 is 1. Let's work that out. U squared over 4 plus 9v squared over 36 equals 1. So that is u squared over 4 plus v squared over 4 is 1. And so u squared plus v squared equals 4. This is your new region. Right, this is a circle. A lot easier than the ellipse, right? You know how to integrate over a circle. The easiest way, as I said before, to integrate over a circle is to use polar coordinates. Okay, so if you had to integrate over this, and it is a whole circle, then you would have r going from 0 to 2, very good, because there's a 4, and theta would be from 0 to 2 pi. Okay? So the new region is a circle of radius 2, center the origin. Okay? As the first one, let's continue. R is the region bounded by y equals minus x plus 4, y equals x plus 1, y equals x over 3 minus 4 over 3. And the transformation that you are going to use to transform that region is x equals a half u plus v and y equals a half u minus v. Now the first thing that I want you to see is what this whole region R looks like. Okay, and why it's advisable to use that transformation. So let me show you what it looks like. Okay, so I'll just tell you, okay? Let me just put in 1, 2, 3, 4. 1, 2, 3. Minus 1, minus 2, minus 3, minus 4. Minus 1, minus 2, minus 3. So let's get the point 3 halves, 5 halves. It's about here. Then 4, 0. Then I want minus 7 halves, minus 5 halves, which is here. Okay, and so let me draw it in blue. So this line here is y equals x plus 1. This one here is y equals minus x plus 4. And this one here is y equals x over 3 minus 4 over 3. And this is the region R. Now let me show you why it would be a little challenging to integrate over that region. If it was horizontally simple, look at what's going to happen. Let me take my black. If I draw a line here, right, a horizontal line, it would go touch these two lines on the top. But at the bottom, touch two other lines, which means we'll have to have two integrals. And do the same thing for vertically simple, you see? Here and here. All right? So it would be difficult to integrate over this. Now let's use the transformation. Let us take the transformation, the equations for the transformation, and substitute it into each of these three equations. Let's see what we get. So let's start off with y equals minus x plus 4. This line. Let's substitute what we have there for y and x. So we have a half times u minus v equals minus x, that's minus a half, times u plus v plus 4. Okay, let's work that out and see what we get. A half u minus a half v equals minus a half u minus a half v plus 4. And when you work that out, you'll get u equals 4. So the first line is transformed to u equals 4. Next line. Let's take y equals x plus 1. See what we get. Y equals x plus 1. Do the substitution again. A half times u minus v equals a half times u plus v plus 1. A half u minus a half v equals a half u plus a half v plus 1, and that gives us v equals minus 1. Not bad. Here we have horizontal and vertical lines. And finally, let's take the last one. The last line is y equals x over 3 minus 4 over 3. So we have a half times u minus v equals x over 3, which is 1 over 6, times u plus v minus 4/3 a half u minus a half v equals 1/6 u plus 1/6 v minus 4/3. And when you simplify this, you get v equals u over 2 plus 2. A half u plus 2. Now let's draw this region. Let's see what this new region looks like. So you're now in the UV plane. So you will put u on the horizontal axis and v on the vertical axis. How much space do I have here? I think we can do it. U, v. Okay, so we want u equals 4. So let's go up to 4. You want v equals minus 1. Let's go down to minus 1. And then you want to draw the line v equals u over 2 plus 2. Okay, so this is u equals 4. V equals minus 1. V equals u over 2 plus 2 goes through 2. And when v is 0, minus 4, is it? When v is 0, minus u over 2 equals 2. So use minus 4. 1, 2, 3, 4. Okay, let me extend this a bit here. Okay, so it should be a straight line. So let me outline this in red now so you can see what I'm doing here. So the region is here, here, this is your new region. And as you can see, this is so much easier to integrate over. Okay? All right. Any questions? Yes. Very good question. So the question was, will you always be given the transformation? No. Sometimes you'll have to deduce it, and then I will show you how you get it. Okay? Very good question. Okay. So I won't do any more questions on transforming regions because we're going to do them anyway. I'm just showing you the steps. All right? So the first thing I showed you is how to find Jacobians. The next thing I showed you was why we using a transformation, why we using a change of variables to show you that the region, the new region, is going to be a simpler region to integrate over. Good. Now I am going to give you the theorem for the change of variables. All right. So that is how you are going to change variables. Suppose R is a closed bounded region of the XY plane and S is a closed bounded region of the UV plane. So important, the regions have to be closed and bounded. They cannot be open. R is the old region, S is the new region. So here's the transformation. So let X be a function of U and V and Y equals G of U and V. So these are your transformations, okay? So let me just make a note of that. So here, that's your transformations. And then R is the old region. And then S is your new region. If your function f is continuous on the region R and your partials, your four first partials are continuous functions, then, let me go back to my black, the double integral over R of capital F of xy is equal to the double integral over S of capital F of fu of v, g of u of v. Now, all of this, what did I do here? What is this? That's just substitution. So here, we have written the function in terms of u and v. So write integrand in terms of u and v, and then multiply, note what you multiply by, the absolute value of the Jacobian. Very important, okay? So you multiply by the absolute value of the Jacobian. Okay? So this is the theorem that we are going to use from now on. Okay. All right, so what I'm going to do now, we're going to do a variety of examples, and if you notice in quite a few of the examples, no transformation is given. So I'll show you how to do that. So let's start with number 1. Let R be the parallelogram bounded by the lines x plus y equals 1, x plus y equals 2, 2x minus 3y equals 2, 2x minus 3y equals 5. Find the area of R given by the double integral of dA. Okay? Now, okay, we need to put a little R underneath there. Sorry about that. Now, by the way, you do not have to draw the old region, right? You don't have to draw any region. I only did it before to show you how the regions are simplified. But you don't need to draw, okay? Right. Now, you look at the lines. Let's find the transformation. If you look at the lines, see what is common. There are two common things happening there. What do you see? X plus y is common and 2x minus 3y is common. So these are going to be your u and v. Okay? So that's how you do it. So u is going to be x plus y. V is going to be 2x minus 3y. Now, I am going to show you two methods to find the Jacobian. Right? Now, the formula that I gave you for the Jacobian, you have to express x and y in terms of u and v, not as is written there. You with me? Right? So, you can do two things. So, the first thing that you can do is to solve for x and y. find what x is, find what y is, and find the Jacobian. Good? So let's do that. So method A. So the Jacobian, let's find that first. Method A. So we need to solve for x and y. In other words, express x and y in terms of u and v. So you do this by simple, like you're solving these two equations simultaneously. So let me set them up. So you have v equals 2x minus 3y, u equals x plus y. So what you can do is that you can eliminate one of the variables. So if I multiply this one by 2, I can eliminate. So v equals 2x minus 3y, 2u equals 2x plus 2y. Subtract v minus 2u equals minus 5y. So we have an equation for y. Y is therefore 1/5 of 2u minus v. Any questions here? I hope I didn't make any errors here. It looks good. Now take this y and substitute it in any of the equations to find u. I think I substituted into the u equals x plus y, right? So u equals x plus 1/5 times 2u minus v, and solve for x. So x equals u minus 2 over 5u plus 1 over 5v. So x equals 3/5 u plus 1/5 v. Okay? So now we have x and y in terms of u and v. Now you can find the Jacobian. Any questions here? Okay, so the Jacobian is partial or delta xy delta uv, determinant partial x partial u partial x partial v partial y partial u partial y partial v. What is partial x partial u, please? 3/5. Partial x partial v? 1/5. Partial y partial u? 2/5. Partial y partial v? Negative 1/5. Okay, what's that? Minus 3 over 25 minus 2 over 25, which is minus 1/5. Okay? So that was method A. Let me outline that here. Method B, which is easier. So I wanted to do the longer method first to show you why you should opt for this second method. Method B. Instead of writing or simplifying or solving these two equations to find x and y, use the equations as is. Don't do anything with them. Just leave them as is, right? Like that. And then, instead of finding j, find 1 over j. Okay? So let me show you what I mean by that. So you find 1 over the Jacobian. So you treat it as a fraction. So that is just delta uv over delta xy. Okay? So you find the reciprocal. So set up your new determinant. partial u partial x, partial u partial y, partial v partial x, partial v partial y. What is partial u partial x? Partial u partial y, partial v partial x, partial v partial y, minus 3. Work that out. Minus 3 minus 2 is minus 5. But this is 1 over j. So j is minus 1/5. As you can see, this is a lot easier, right, than doing it the other way. Okay? All right, so we have j. Now we're ready to, the other thing that we need to do is to write up the new lines. Okay, so what did we have originally? We had x plus y equals 1. That becomes, our x plus y was u, right? Was x plus y u? Yes. So that becomes u equals 1. What else we had? X plus y equals 2. That becomes u equals 2. Next. 2x plus 3y equals 2. That now becomes v equals 2. And finally, 2x minus 3y equals 5. That becomes v equals 5. So these are our u limits and these are our v limits. And as you can see, because they are all constants, we are integrating over a rectangle. Okay? So let's set up the integral and let's work it out. So this is what we had to find. The area, which was given by the double integral over r dA. We have transformed the region. So now write your new integrals. So you can put, it's a rectangle, so I'll put u on the inside. We'll put it later. Let's do the integrand. The integrand is just 1, but you need to multiply by the absolute value of the Jacobian. So absolute value of negative 1/5 du dv. Put your limits. U limits 1 to 2, v limits 2 to 5. Okay? This is so much easier to integrate, all right, than integrating over this parallelogram. Okay, let's simplify that. Oh, I don't have much space. 2 to 5, 1 to 2. That is just 1/5 du dv. Okay, integrate 2 to 5. The integral of 1/5 is 1/5 u. U goes from 1 to 2 dv, which is equal to 2 to 5, 2/5 minus 1/5 dv, which is equal to the integral from 2 to 5, 1/5 dv, integrate 1/5 v from 2 to 5, 1 minus 2/5, which is 3/5. So that was the area of the parallelogram. Any questions on this problem? So these questions are quite long, all right? But if you do them, take them one step at a time, find the transformation, find the Jacobian, find the new region, set up your integral, you are fine. Okay?
Can either method be used for any problem?
Yes, you can use either methods, okay, to find the Jacobian. Most times, as I said, it's easier to find 1 over j first. Okay? Okay. Next question. Use the transformation u equals xy and v equals y over x. So here I've given you the transformation. To evaluate the double integral over r, don't forget our little r below here, of x cubed y dA, where r is the region in the first quadrant bounded by y equals x, y equals 2 over x, xy equals 1, xy equals 3. Okay, so our transformations are u equals xy and v equals y over x. Let's transform this region and then we'll find Jacobian, okay? So what does y equals x become? Look at it closely. Which of them are we going to use? Which of the transformations? V equals y over x, right? So if y equals x, what is v? 1. Okay, so this implies that y over x is 1. So this implies that v equals 1. What about y equals 2x? What is v here? 2. So this implies that y over x is 2. So v equals 2. Alright? So the v's are taken care of. What about the other two? xy equals 1. That one is easy. That tells me that u is 1. xy equals 3. That tells me that u is 3. Alright, so we have moved from this strange region to a region which is a rectangle. Alright. Shall we find the Jacobian? Now again, I'm going to use method B and find 1 over j. Alright, because we have u equals xy and v equals y over x. So 1 over j equals delta uv delta xy, which is the determinant of partial u, partial x, partial u, partial y, partial v, partial x, partial v, partial y, which is equal to, what is partial u, partial x? Y. Are you asleep? What is partial u, partial y? X. Okay, some people are waking up. What is partial v, partial x? Oh, more people are joining the fun. And what is partial v, partial y? 1 over x. Nice job. Let's work that out. That's y over x minus minus plus y over x, which is 2y over x. Now, the Jacobian is in terms of y over x. We don't want that, right? Remember, we're transforming. So we need to change to u over v, u or v or both, which is 2v. And don't forget, we are finding j. So j is 1 over 2v. Okay. All right, let's look at this now. Now look at what we have to integrate, everybody. We have to integrate x cubed y, right? But we need to transform this. We have to transform it to u and v. So therefore, we have to go back to our transformations and find what x and y are anyway. All right? So we need to solve for x and y. Solve for x and y. Okay, so what do we have here? U equals xy, v equals y over x. All right, we can solve this in so many ways. One way we can do, and the reason I know we can do it that way, because u is a product of x and y, v is a quotient of y over x. Why don't we multiply the two? Find uv. What do you get? uv is y squared. So we already have y, square root of uv. Right? So I'm teaching you little tricks to solve. Huh? And then you can also divide. What is u over v? U divided by v. What's that? X squared. So this implies x equals square root of u over v. And so let's transform the integrand. So the integrand is, what is it? X cubed y. So let's write it now in terms of u and v. So that is equal to x cubed would be u over v to the 3/2 times y. Y is u to the half, v to the half. And when you work this out, you get u squared over v. So we have all what we need, okay? We have transformed the region, we have found the Jacobian, we have transformed the integrand. Now set up the integral. So the double integral, is it over r of x cubed y dA, is the double integral. The integrand becomes u squared over v times absolute value of the Jacobian is the same, 1 over 2v, du dv. What are the limits for u? I don't want to scroll up again. What's it? 1 to 3, thanks. And what are the limits for v? 1 to 2. Okay? So simplify this integrand. 1 to 2, 1 to 3. What is this? U squared over 2v squared du dv. Okay. First, integrate with respect to u. When you integrate with respect to u, what do we have here? Very good. U cubed over 6v squared. U goes from 1 to 3. Substitute u equals 3. That's 27 over 6v squared minus 1 over 6v squared dv. Which is equal to the integral from 1 to 2, 26 over 6v squared dv. Let me just simplify this to 13 over 3v squared dv. And when you integrate this, you get minus 13 over 3v from 1 to 2. Which is equal to minus 13 over 6 minus, that's plus 13 over 3, which gives us 13 over 6. Okay. Next, another one. Evaluate the double integral over r of x squared plus y squared dA, where R is the region bounded by these. Okay. No transformation was given here, right? Can you suggest? X squared minus y squared, and what is V? Okay, now this one is a little tricky, and I'll tell you why I'm choosing a different transformation for V in a little while. All right? Instead of V equals xy, I'm going to choose V equals 2xy, and you will see why I chose 2. Okay? I will explain it in a little while. Okay, let's transform the region before we find Jacobians. So what is the region, the new region, going to be? X squared minus y squared equals 1, and x squared minus y squared equals 9 becomes u equals 1 and u equals 9. And then xy equals 2 and xy equals 4 becomes what? 2xy is V, you know. Careful. If xy is 2, what is 2xy? 4. So what is V? Careful, careful. Okay, let's do this again. V equals 2xy, right? So we need to convert these two equations to 2xy. Good? So if xy equals 2, what is 2xy here? 4. And what is 2xy here? 8. So now give me your limits for V. 4 and 8. So careful. Sometimes when you do things in your head, you make mistakes. So you write them, okay? So we have our limits. And as you can see, it's over a lovely rectangle again. Shall we go for the Jacobian? Let's do it. Do you want to do 1 over j or j? Let's do it. So 1 over j is partial uv partial xy determinant partial u partial x partial u partial y partial v partial x partial v partial y. Can you give me the partials? Partial u partial x, 2x, partial u partial y, partial v partial x, partial v partial y, 2x. Okay, what do we have here? 4x squared plus 4y squared. Aha. That is 4 times x squared plus y squared. Right? Now, we need to change that back, right? We need to change it back to u and v. But there's nothing there in our transformations that's going to help us. And we also need it for the integrand. You realize that x squared plus y squared is the integrand. So we have to solve x squared plus y squared in terms of u and v. Now that is where it gets tricky. I put this question in there because it's a difficult one. Look at the transformations that we have. We need to find, let me just write what we're doing. We need to write x squared plus y squared in terms of u and v. That's what we're trying to do. Go back to your transformations. U equals x squared minus y squared. V equals 2xy. And now you will see why I put the 2. That's the only way we could get, we could write x squared plus y squared in terms of u and v using the transformations. Anybody, now this is a difficult question, but let me see if anybody has any clue as to what I can do. I need to solve. I need x squared plus y squared. How can I get that there from these two transformations? Any suggestions? Somebody said u squared? Somebody said u squared. You're on the right track. Let's try u squared. U squared. Find u squared. What do you get? Just square this. You get x to the fourth minus 2x squared y squared plus y to the fourth. We're getting somewhere. You had to do something with u squared, but what else do we do? So you're on the right track. Beautiful, whoever said so. What else can we do? Find v squared. Beautiful. Oh, this is so fantastic. Find v squared. 4x squared y squared. And then somebody said add v squared. So you get u squared plus v squared, which is x to the fourth plus 2x squared y squared plus y to the fourth. Where are we going with this? This is equal to what? Very good. This is equal to x squared plus y squared squared. Now, do you see, if I did not have v equals 2xy, I would not be able to get that. If I had just written v equals xy, I would not be able to arrive at what I just did. So that is why I put the 2xy in there. Originally, when I first saw this question and I was working it out, I chose xy because it seemed obvious, right? But when I tried working it out, no way could I find what x squared plus y squared was. So I went back and I said, let's try 2xy. And I got it.
So it's just trial and error?
Well, that was trial and error. Well, yeah.
How do we identify that?
Yeah, yes. I would love that, wouldn't you?
No.
That's a beautiful question for an exam, actually. But if you get a question, since you're doing this for the first time, and if I had to set a question like that on the exam, I would give you the transformation. Okay, I wouldn't expect you to reason this out in 2 hours. Okay, that's unfair to you. Okay? So where are we? What were we doing now? So therefore, x squared plus y squared is the square root of u squared plus v squared. Okay? And so this tells me that 1 over j is 4 times the square root of u squared plus v squared, implying that j is 1 over 4 times the square root of u squared plus v squared. Alright, so what have we done? We have written down the transformation. We have found the Jacobian in terms of u and v. We have actually transformed the integrand. So now we're ready to write the integral and evaluate. So the integral is, what was it again? The double integral over r of x squared plus y squared dA. Okay, transform. So x squared plus y squared is square root of u squared plus v squared times the absolute value of the Jacobian, which is 1 over 4 times the square root of u squared plus v squared du dv. Can you give me my u limits, please? And v 4 to 8. Okay, simplify that. Integral from 4 to 8, integral from 1 to 9, a quarter du dv which is equal to integral from 4 to 8, a quarter u, from u equals 1 to u equals 9 dv, which is equal to the integral from 4 to 8, 9 over 4 minus 1 over 4 dv, which is the integral from 4 to 8 of 2 dv, which is equal to 2v from 4 to 8, 16 minus 8, which is 8. Okay. Yes. You are transforming. Okay, that's a good question. If you can leave everything in terms of x and y. Well, you could, because it was a very easy question here, so the x squared plus y squared could have cancelled. But in the event that it is not that easy, I actually wanted you to transform it. So just in case, you see, if you had left everything in terms of x squared plus y squared, the Jacobian, because you have an x squared plus y squared in the integrand, they cancel. But what if you did not have an x squared plus y squared? So I wanted to show you the trick of doing that. But yes, for this particular question, it could have been done. Okay, let's move on. Number 4. So I think I'm going to do this one, and then it's your turn, I hope. My lips are getting a little tired. Okay, now let's look at this. That's a very interesting one. And I hope I have enough space for that one. Evaluate the double integral, my little r is missing as usual, of x plus y dA. R is the trapezoidal region with vertices given by 0, 0, 5, 0, 5 halves, 5 halves, and 5 halves, negative 5 halves, using the transformation x equals 2u plus 3v and y equals 2u minus 3v. So here we are given the transformation. What are we not given here that we were given previously? All the equations for the lines or curves, whatever, they're not given here. We have to find them. So what do we need to do? We need to draw that region, okay, and then find the lines. So let me put that on the side there, because I don't think I left enough space for this question. Okay, so we need 0, 0. 1, 2, 3, 4. 5. 1, 2, 3. 1, 2, 3. So we need 5, 0. We need 5 halves, 5 halves. And we need 5 halves, negative 5 halves. Oh, okay. Now, you know you need to find the equations of the line. So this is just simple algebra. Find the slope and write the equation of the lines. So let me write them on each line. So this is from 0, 0 to 5 halves, 5 halves. The slope is what? 5 halves over 5, 1. And so this line is y equals x. So this one is y equals negative x, beautiful. This third one is parallel to y equals x. And it passes through y 0, so that's y equals x minus 5. And then this one is y equals minus x plus 5. Okay, so you need to do that, all right? After you have done that, transform the lines. So y equals x becomes, so do the substitutions like I did in the previous question. 2u minus 3v equals 2u plus 3v. Here we end up with v equals 0. Y equals minus x is similar. 2u minus 3v equals minus 2u minus 3v. We end up with u equals 0. Y equals minus x plus 5 gives us 2u minus 3v equals minus 2u minus 3v plus 5. We end up here with u equals 5 over 4. And then y equals x minus 5 gives me 2u minus 3v equals 2u plus 3v minus 5. We get v equals 5, 6. So we have our u and our v limits. Okay? What's our next step? Jacobian. Okay, so let's do our 1 over j. No, we don't need to do 1 over j, right? It's x and y given there, so we just need j. It gives us j right away. That's beautiful. Partial xy, partial uv, determinant, partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Okay, what is that? Partial x, partial u, that's a 2, 3, 2, minus 3, which is minus 6, minus 6, which is minus 12. Okay. We have our Jacobian. What is the next step? Transform the integrand. So the integrand is x plus y. So just substitute the x and the y's. That's 2u plus 3v plus 2u minus 3v, which is 4u. Okay, we're ready. Let's transform. So we have the double integral over r of x plus y dA is the double integral. The integrand becomes 4u times the absolute value of the Jacobian, which is negative 12, du dv. Our u limits 0 to 5/4. V limits 0 to 5 over 6. Okay, let's simplify that integrand. That is 0 to 5/6, 0 to 5/4 of 48u du dv. The integral from 0 to 5/6, integrate 24u squared from 0 to 5/4 dv. Okay. When you work that out, you will get 75 over 2 dv. And your final answer is 125 over 4. Okay, that's a very good question. For a question like this, the question was asked, when you have reached the double integral, can you just put it into your calculator? Yes, I would allow it. That'd be okay. Is it due now? Okay, your turn. I think, would you like to do it together? Okay, well, you tell me what to do and I write, okay? All right. So put your little r there, that is missing. The double integral over f x dA, where r is a region enclosed by 2x minus y equals 0, 2x minus y equals 4, x plus y equals 0, and x plus y equals 3, and use these change of variables. Okay, what is the first step? Tell me. You are changing the lines, okay? So what are they? What do the lines become? U equals 0, U equals 4, V equals 0, V equals 3. Okay. What is the next step? Jacobian. So how would you like to find the Jacobian? 1 over j. Good. So set it up. Set up the fraction. Del uv del xy. Set up your determinant. Partial u partial x. Partial u partial y. Partial v partial x. Partial v partial y. And then give me the components there of the matrix. 2, negative 1, 1, 1. Work out the determinant. Tell me what you get. 2 plus 1, which is 3. And so what is j? 1/3. Beautiful. What do we do now? You ready to integrate already? Find what? The integrand, which is x, yeah? Now, how do we find x? So, find the integrand x. But we need to write x in terms of u and v. Look at the two transformations. U equals 2x minus y. V equals x plus y. How can I find x from these two? Just add them together. Beautiful. Okay? So when you add these together, let me put that in when you add this together, you get u plus v equals 3x. So x is 1/3 of u plus v. Okay? Nice. Are we ready? Let's set up the integral now. Double integral over r of x dA becomes double integral. What do we have? 1/3 u plus v. Continue. Times what? Times 1/3 du dv. Limits, please. U limits are what? And v limits. Okay. I would put that 1/9 outside. u plus v du dv. Okay, let's see what that is. Anybody worked it out? When you get it, tell me. You can do it, put it into your calculator. Are you ready? You got 14 over 3? I don't know. I didn't work it. I'm relying on you.
I got 42 over 9. So.
Aye, aye, aye. So, okay. One got 42 over 9. One got 14 over 3. It's the same. Oh, yeah.
I just did it without simplifying.
14 over 3. Sweet. Okay. So that's the change of variables when you have a double integral. Oh, there's another one. Let's do this other one together. And then we will end with triple integrals. Okay? So this one, you have to draw it. All right? Let's draw. So we need 0, 0, 2, 1, and 1, 2. 2, 2, 1, 1, 2. Okay. Now you need to find the equations of these lines, and I'm glad I'm doing this because this one is a little different from what we have done in the past. So let's do this together. All right, now what is the equation? So you need to find this. The equation of this line, y equals 2x. This one is y equals a half x. Good job. And this one is x plus y equals 3. Or y equals, what am I doing here? Or y equals 3 minus x. Okay? Good. So we have drawn the region. Now let's transform it. Okay? So take these lines and substitute your u and v equations into there. So let's do that. Oops. So y equals 2x becomes u plus 2v equals 2 times 2u plus v. And when you work that out, you'll get u equals 0. Y equals a half x. You have u plus 2v is a half times 2u plus v. When you work that out, you get v equals 0. And x plus y equals 3 gives 2u plus v plus u plus 2v equals 3. This gives u plus v equals 1. So you see what is happening there, why I really inserted this question into this lecture. all the new regions that we had before, they were all rectangles, huh? Look at what we get in here. We have a triangle. So here, this new region, you have to draw it, because right now, when you're setting up the integral, you will have to decide whether you want it to be horizontally or vertically simple. Okay, so let's draw this new region. So now we're in the UV plane. We need to draw the line u plus v equals 1. So it just passes through 1 and 1 here. Okay, so this is the line. So this line, let's call it v equals 1 minus u. So you decide. Either would work, horizontally or vertically simple will work. It does not matter which. So let's make it vertically simple. Okay. And then we will set up our integral in a little bit. There's one thing we forgot to do. Let's do the Jacobian. Okay? So we will set up our integral in a little while, all right? Jacobian now. Okay, so I think we can find j right away. Good. So j is delta xy delta uv, determinant delta x delta u delta x delta v delta y delta u delta y delta v. Give me the partials in there, please. 2, 1, 1, 2, which is 4 minus 1, which is 3. Okay. Next step. Integrand. X minus 3y, so you just substitute what x and y both are. So that is 2u plus v minus 3 times u plus 2v, which works out to be minus u minus 5v. Okay. We ready? Let's transform. The double integral over r of x minus 3y dA. The double integral of minus u minus 5v times 3. Because it is vertically simple, we need to put it as dv du. So be careful, all right? Make a note on that. Put it on your sheet that we have dv du because it is vertically simple. I will write it here as well, because you don't want to get confused there. Okay? Vertically simple. What are our u limits? 0 to 1. V limits 0 to 1 minus u. Good. And when you work that out, you get minus 3. Okay. I will end with a brief look at triple integrals, the Jacobians for triple integrals. Okay? Okay, I'm missing another integral here. Please put it in. We need another integral here. So let's put this old region R, new region S. So as you can see, it is the same transformation, except look at the Jacobian. It's now a 3 by 3 matrix because you have 3 variables. Okay? So that's the only difference. So let us work this one out, and that would be it. Find the triple integral over E, put E below there, of y dv, where E is the solid enclosed by the planes 2x plus y equals 0, 2x plus y equals 3, x minus z equals 0, x minus z equals 2, z equals 0, z equals 4. Now the way it is set out for you, the transformations are clear. So our transformations are u equals 2x plus y, v equals x minus z, w equals z. So based on this, this transforms to u equals 0, u equals 3, v equals 0, v equals 2, z, not z, w, w equals 0, w equals 4. Now let's find the Jacobian. We now going to use 1 over j because we have u, v, and w in terms of x, y, and z. So 1 over j is delta u, v, w over delta x, y, z, which is the determinant, partial u, partial x, partial u, partial y, partial u, partial z. So put all the u's in one row. Go to the v, partial x, partial v, partial y, partial v, partial z, and then partial w, partial x, partial w, partial y, partial w, partial z. Now you find all the partials, and they are 2, 1, 0, 1, 0, minus 1, 0, 0, 1, and you put that into your calculator and you get minus 1. And so j is also minus 1. Now we need to transform the integrand, which is y. Okay? So we need to solve for y. Let me number these 3 equations. 1, 2, 3. The only place we have y is in the first equation. So if we have what x is, we can solve for y. So take 2 and 3 and add 2 and 3. So 2 plus 3 gives v plus w equals x. So we have found x in terms of v and w. Substitute it into 1 to solve for y. So u equals 2 times v plus w plus y. So y equals u minus 2v minus 2w. So this is the integrand. Okay, set up your integral now. The triple integral over e of y dv. Y is u minus 2v minus 2w The Jacobian is -1. Absolute value is just 1, so we don't need it. du, dv, dw, 0 to 3, 0 to 2, 0 to 4. Let's integrate this. With a triple integral, I would want you to integrate it. Okay, 0 to 4, 0 to 2, integrate with respect to u squared over 2 minus 2uv minus 2uw from u equals 0 to 3, dv dw, work that out, 0 to 4, 0 to 2, 9 over 2 minus 6v minus 6w dv dw integrate with respect to v, 0 to 4, 9 over 2v minus 3v squared minus 6wv, v equals 0 to v equals 2. This becomes 0 to 4 of minus 3 minus 12w, which ends up being minus 108. Any questions on that? Thank you.